Today I'd like to talk about work and the calculus approach to calculating work. It'll kind of introduce an idea of what that would mean. So imagine here that I have a car, something like this. Doesn't have to look great. And my car's broken down because it doesn't look very good. And so I need to move it over. And as I'm moving it over, of course I'm exerting work. And so I have to put a force onto the car. And here I'm assuming I have a constant force. And I'm having to move that car some distance. So that's a great way to think of work. Actually, we calculate work by saying, so work is a force times a distance. And it may also be worth remembering that force is calculated as a mass times acceleration. And we calculate mass as a density. Let's see, we use little m or ma as density times a volume. Alright, so all those things are important when you're talking about work, and how this fits into calculus is if you have a force function, so f of x is the force moving something x units on an interval a to b, then our work is actually the integral of f of x dx. And this will become apparent why in some of our examples. You'll notice is that we use Riemann sums a lot. Now you might need some unit measurements. So let me go ahead and write those down. I'll write them in the standard or US standard and then the international standard. Okay, so in the US customary system we use feet for distance, pounds for force, foot-pounds for work. And that does say foot-pounds. In the international standard we use meters for distance, newtons for force, and newton meters or joules for work. And so we'll commonly use joules here. Alright, so now as an example, of work, here we have a 1,000-foot length of steel chain weighing 15 pounds a foot is dangling from a pulley. We want to know how much work is required to pull the pulley up, or the chain up onto the pulley. So let's get a picture of this. So we have some sort of pulley hanging out here, and we have this chain dangling down, and we want to wound it up. Alright, so we have to remember again that your work is your force times distance. And the way we're going to approach this is actually by calculating maybe just this segment. How much work is required just to move that segment of the chain up? So to do that, I need to get some sort of axis system. So we'll let x be kind of the depth. So we have x going from 0 to 1,000. And let me widen my interval a little bit, just so we can visualize it a little better. So let's say I'm moving this interval here. So what I want to do is I'm going to consider some sort of delta x, and that's the length of this segment I have. And then I need to pick some sort of representative in here to kind of calculate the work being done at that point. And so I'm going to have an xi star, and that may sound familiar if you've dealt with Riemann sums before. Alright, now for a force, so here by Wi, I mean the work on segment I. Okay, so that's this part here. How much work is being done to calculate that. So that's what I mean by WI. So I need a force, and my force is my weight, right? Pounds is a measurement of force. And here I know that this thing is weighing 15 feet a pound, or 15 pounds a feet, sorry. And delta x is some unit of pounds, or some unit of feet, I'm sorry. So here I have 15 delta x as my force. That's 15 15 pounds of feet, let me see if I can say this right, times delta x, which is in feet, so we get 15 pounds. And the distance traveled by this segment is where I get my xi star. That's how far this segment has to travel. So there I have xi star. So there's my my wi. So now if I want to calculate work, I want to calculate capital W work, well, that's going to be the sum of all my wi's. And it's a smart idea if I just get smaller and smaller segments each time, I'll get a more accurate measurement. So how do I do that? Let's take the limit, this n goes infinity, of the sum, starting with 1, going up to, going up to n of these wi's. So that's going to be the limit as n goes infinity, the sum, and I going from 1 to n of 15 xi star delta x. Right, that's what I calculated here. And we know from experience that when you take the limit of a sum like this, you end up with an integral. So this is the integral going from 0 to 1,000 of 15x dx. So that's not too hard to calculate. We know the integral of x, that's going to be 15x squared over 2, going from 1,000 to 0. So then you have 15 halves times 1,000 squared. And you can just put that in your calculator, and this will be a measurement of joules. And that's the amount of work it required to move the chain all the way up onto the pulley. What am I actually saying here? We're measuring this using the English version of measurement, so we're not talking about joules, right? We measure this in foot-pounds. Sorry about that, I'm just being a little careless. Now another common theme in a calculus text with work is Hooke's law. The reason Hooke's law is so great for us is that here we have Hooke's law. The force required to stretch a spring x units beyond its length at rest is linear. In other words, we can calculate the force function as just kx, so multiplied by x. So for that reason, it's easy to introduce examples like this. A spring exerts a force of 6 newtons when it's stretched from its natural length of 4 meters to a length of 4.5 meters. Okay, so we have this spring. We have this spring like this. If we don't mess with it, it's 4 meters long. But now when I want to expand it out to 4.5 meters, it takes 6 newtons to do that. Alright, so the question is what's the work required to go from its natural length to 6 meters? Okay, so we need this first part here, talking about the half meter part, to help us figure out what k is in this instance. So what we know is that if I plug in, well, let's see, I stretch from 4 to 4 to 4.5 meters. So I want to plug in 0.5, right? Because it says here in Hooke's law, beyond its length at rest. So that's 0.5 meters beyond the length of its rest. Oh, you know I get a force of 6. And I know that's the same thing as k times 0.5 by Hooke's law. So there we have that k is actually 12. So there's what I call n physics, this is called the spring constant, or your spring coefficient is another word for it. Okay, so now that we know that my force function is actually 12x. So then the question is, find the work required for the spring to go from its natural length to 6 meters. And so work, remember, is just an integral. Here we're going 2 meters beyond our natural length, so we're going from 0 to 2, 12x dx. And that's about as simple as an integral as you can get. And we end up with 6x squared, 0 to 2, which would be 24 joules.